Hello and welcome to another SciTechNature. It is April the 14th and we've got a lot of exciting stuff today. So without further ado, let's get going. So I'd like to start off with a little bit of thought candy. A little bit of science, a little bit of fantasia and imagination. Sort of touches upon the idea of parallel universes, and it's only 2 minutes long, and it satisfies my craving for that kind of stuff for a day. Disclaimer, the infinite zoom video we just saw, down below is the link. The first part of it is pretty correct. Then they go into the eye and into some depth, and then it goes into a little bit of the imagination, which I actually love. And it goes deeper and deeper and deeper into it. And then suddenly you're out in the galaxies, and there we are back into reality again. And then it goes, of course, back to the Earth, or a parallel Earth. Who knows what the author was thinking. But I just thought I'd point that out so you wouldn't take it all for hard fact. All right, let's move on. I came across this article the other day, which describes the journey of the Voyager and the Pioneer spacecraft and how they're journeying out and how they may not be getting completely away from the solar system for a considerable while due to something called the Oort Cloud. The Oort Cloud is far, far away from our solar system. And to give you a clearer idea of the Oort Cloud, I found this video that you might find interesting.
Short-period comets visit the sun so often that they quickly evaporate, vanishing in only a few 100,000 years. Here's one that evaporated in the Sun's corona in July 2011. It was traveling at 644 kilometers per second. That's 400 miles per second. Here we see it in time-lapse from the Solar Dynamics Observatory. The comet enters on the right in this video. In this second pass, I've marked it along the way. It starts out with the mass of an aircraft carrier, and it's completely evaporated in 20 minutes by the searing heat of the Sun's corona. They evaporate so quickly, compared to the age of the solar system, that we shouldn't see any left at all. Yet, we routinely track dozens of them every year. In 1951, Gerard Kuiper proposed that there must be a belt of icy bodies orbiting beyond Neptune that is the source for new comets. It is much further away, much larger, and far less dense than the asteroid belt. It starts at 30 astronomical units from the Sun and is 20 astronomical units wide. 1992 QB1 was the first Kuiper belt object. In 2002, a large KBO, hundreds of kilometers in diameter, named Kuawa, was found. In 2004, KBO Sedna was discovered. And we have seen that Pluto and Makemake are dwarf planet KBOs. It is estimated that the Kuiper belt contains 100 million comets. In 1950, in order to explain long-period orbits, the Dutch astronomer Jan Oort proposed the existence of a cloud of comets between 5,000 and 55,000 astronomical units from the Sun. Other estimates have it going out much further. All estimates put the Oort Cloud well outside the heliosphere. Oort estimated that this reservoir contains 100 billion comets, maybe 1 trillion. Citing Spring, Hale-Bopp, and Lovejoy 2014 are 3 of them. No space probe has yet been sent to the area of the Oort Cloud. Voyager 1, in the heliosheath, is traveling at 1.6 million kilometers per day. That's 1 million miles per day. It will take over 1,200 years just to reach the Oort Cloud, and over 12,000 years to pass through it. So its existence will remain a theory for some time to come.
So the Oort Cloud is a very feasible possibility. It's still a theory. It's a strong theory, but it's still a theory. There is always a tendency for many scientists and laymen alike to slip into talking about things as if they're well-founded facts. Well, this isn't a well-founded fact, but it's a really interesting and strong theory. And speaking of theories and facts, here we have a very interesting article. A widely held theory about the universe expanding has just been contradicted. Well, that's maybe a little bit too abrupt. What this article is suggesting is that the expanding universe is not expanding at a uniform rate, but kind of like you think of a COVID virus with all the little thingies on it, that it's expanding in different speeds and different directions. All this has to be taken with a grain of salt. These are interesting ideas. They are based on a little bit of evidence and data and a lot of interpretation. Nonetheless, it makes for a great read, and I've placed it down below. We've come a long, long way from the days when the Neanderthals were considered brutish an unintelligent, squat characters that barely were able to survive in their environment. And we've come to now realize by degrees just how sophisticated they were, as is shown by this 50,000-year-old string. Shows that the Neanderthals were technologically advanced. It makes for interesting reading. It's down below, and I'm going to move on to the next item. So we're going to move the clock a little bit further forward in time to the about 12,800 years ago, during a period called the Younger Dryas. We have talked about the Younger Dryas before in earlier presentations. It caused much excitement last year when it was discovered that there's this huge impact that created a crater in Greenland that was some 30 kilometers across, which is enormous. And it has a lot of paleontologists very excited because they've been trying to put together all these pieces as to why all this flora and fauna suddenly disappears, especially in the Americas during this time period. And this impact crater could be responsible for it. They don't know for sure yet. They've done ice drillings, and it looks like the melt at the bottom of this crater are from 12,000 years ago, but the jury is still out. Although, like I say, very, very exciting. And so I thought, apart from this article here, which makes for a really great read, shows how the impact had a global effect. Apart from this article, I want to talk a little bit, or rather have someone else talk a little bit about the demise of the Clovis people, which were the earliest people in the Americas and who suddenly just disappear from the scene around the time of the impact, and the animals that also disappear from this period. So it may be that these huge animals that were around before the impact were not killed by the Clovis people or hunted to death by us humans. Maybe this time we're not to blame. Maybe it's a natural force that caused this to happen. So without further ado, let's listen to a little bit of the lecture. I've spliced a few pieces together, and of course, both will be down here in the links.
We'll look at current knowledge and conjecture about the timing and nature of the earliest appearance of Homo sapiens in North America, and also explore the possible effects that this rapid human migration had on the largest land mammals of the continent. So, with that, let's get started, and I present to you Dr. Gary Haynes.
Thank you very much.
We'll look at current knowledge and conjecture about the timing and nature of the earliest appearance of Homo sapiens in North America, and also explore the possible effects that this rapid human migration had on the largest land mammals of the continent. So, with that, let's get started, and I present to you Dr. Gary Haynes.
Thank you very much. What I want to do here is first start off giving you my bona fides. So I'm going to try to tell you what my background is in a more graphic way than what you've just heard. At the same time these animals became extinct in the mainland of North America, a whole bunch of other animals became extinct. Now, I don't have pictures of them all, but I wanted to show you some of the more impressive ones. This is a giant short-faced bear, which is considerably larger than the biggest brown bear today, which would be Kodiak bear, grizzly bear. And you can see from this 6-foot silhouette here that it stands 6 feet just on all fours. Long legs, short snout, that's why it's called short-faced bear. And we probably, you know, when you look at it, you probably should be grateful. It's like T-Rex, grateful it is extinct, that we don't have to worry about it. But this one disappeared at around the same time period. Here's an African lion, and here's the American lion behind it. And it's bigger than the modern African lion, and these animals can weigh 300 pounds or so. And this is a much bigger animal, and it's extinct also. It became extinct possibly around the same time as the mammoths and mastodons, and there's a whole bunch of different kinds of sloths, giant sloths. Harlan's ground sloth, big sloth. Here's Jefferson's ground sloth. There's a smaller one, Shasta ground sloth, which didn't stand quite as tall as these, became extinct possibly around the same time period as the mammoth and mastodon. And remember, also possibly around the same time period that humans are present throughout the continent. And there was a giant beaver that's about the size of a black bear, 300-pound beaver, that obviously is not the same behaviorally as modern beavers. It doesn't have the big flat tail, but it's enormous, and it's got giant teeth, so it's hard to imagine how its habits differed from the modern beaver, because it's sort of a blown-up version of it, but it must have been different. Now, there's a whole bunch of these other taxa here that became extinct around the time period of these first people, who are sometimes called Clovis, based on the name of the spear point that they made, Clovis projectile points. And Clovis is around 11,200 radiocarbon years ago, or 13,000 real years ago, to maybe 400 years later than that. It's a short-lived kind of phenomenon. Well, most of these animals, you have these late radiocarbon dates that are pretty close to the appearance of that Clovis spear point, the people who made it. This is a cheetah. There was a cheetah. There's the short-faced bear. There's some musk oxen, a camel. We had a one-hump camel. The people called Clovis, the Clovis culture, made spear points like this. And these are made out of high-quality rock that they searched for. It's not everywhere available. They are shaped, lance-shaped, and they have this flake that's been taken off from the base towards the tip on each side, called the flute, the thinning flake at the base. They also made bone points and ivory and antler points like this. The black one here is an ivory, mammoth ivory or mastodon ivory from Florida. Some of these are points maybe on spears. Some of them were used maybe as just linking the stone point to the spear shaft. And if you find these, and you can find them throughout North America, even up here in Alberta there are variants of these, they share the same characteristic: high quality rock, lance-shaped, the fluting or the thinning flake from the base. These are the ones originally found and given the name Clovis from New Mexico. Here's some from Florida, a little bit of a difference, a little bit of waste on it, for example, here. And this is another ivory point fragment. And here's some from Missouri in the United States. Here's some from Illinois. Here's some from Tennessee, some from Virginia, one from Idaho. Lots of similarities, but also a lot of regional variation in them. So they're not all identical. There's some little differences in the spear points, and this is what anthropologists, archaeologists get really excited about, the little differences, between the stone spear points. But there are enough differences in the shapes, could be temporal, could be related to time. People are just changing what they think they should look like, or it could be related to geography. And if you notice the little red dots all over this map, this is where the ones that have been found and reported are located. What we have at 13,000 years ago, and I know I haven't solved the problem, but what we have 13,000 years ago is extinctions, and it looks like every time a new radiocarbon date is run on an inadequately dated taxon that became extinct, it ends up 13,000 years ago. So anything that became extinct 30,000 years ago, according to the literature of 20 years ago, has been redated. It'll probably end up surviving to 13,000 years ago. So we're not talking about long drawn out extinction. It looks like it's really there at 13,000 years ago.
Of course, those were just little snippets of the entire lecture. I personally found it absolutely fascinating that people, the Clovis people and the Megafaunal, all seem to disappear roughly at the same time. And the time that this was recorded was 2018, and it must have been around the time just before the discovery of the Greenland impact was announced. So I would give them high teeth to know what the lecturer would be concluding now, that they have this tantalizing possibility that it all came to a grinding halt due to an impact. All right, well, if I hear any more about this, I will keep you up to date because it tends to fascinate me. Well, let's move on to the next. Bob Lerner and Doug Wynn turned me on to this really set of fascinating discussions between the great minds of our time. And I haven't seen it all yet, but I'm going to. It's quite long. I think it's going on to something like 2 hours, but you won't be bored, and it's really quite a fascinating collection of interviews that are done sort of live. It almost looks like it's done on Zoom, and of course, it's appropriate for the pandemic conditions that we presently have to deal with. So I've created a small collage of the interviews, and they will be following right away.
So we're covering all these different fields, right? Genetics, neuroscience, longevity, microbiome, food, human performance, the future of sex, the future of drugs, the future of death, artificial reproductive technologies. All of these fields are poised to be completely transformed by our new biotech tools. So which of these areas do you personally care about the most? So again, go to our poll. You can check the areas that you're most interested in, whether that's personal interest or perhaps that's the field that you are working in. Just give us a sense of where your focus is. At Neo.Life, we're very focused on Homo sapiens. We're focused on human beings and our relationship to other species and the planet. Others of you may be more focused on climate change, but obviously there's a relationship there, or energy sources. So that's what we're looking for on this question.
A bit more about what his company is doing now and what they're doing to impact our future. So Jason, thank you so much.
Thanks, Jen. So yeah, maybe just a little background on Ginkgo for those of you that don't know. Yes, we're a synthetic biology company, and the core idea behind Ginkgo is we'll program cells like we program computers because they run on digital code in the form of DNA, right? So it's ATCs and Gs, not zeros and ones. But you can read this code with DNA sequencing, and you can write it with DNA synthesis or DNA printing. And if you can read and write code, and you have a machine to run it, that's programming. And Ginkgo is now the largest printer of DNA in the world. So about 25% of the genes that are printed worldwide are designed by us. And, it's been an interesting experience. The last 5 years, we've raised about $800 million, scaled out a lot of facilities to do all that genetic engineering, DNA printing. But, I got in the field now almost 20 years ago. So when I first met George and others and the co-founders of the company back at MIT. And we had this weird experience where we were really passionate about engineering biology, and we're like, biology's so amazing, it's so powerful, and everyone is kind of like completely takes biology for granted, right? Like they're like, whatever, it's not that important, and I'm like, but it makes the atmosphere and it makes all our food, and you plant a seed and you grow a plant, it's like solar panels, it's incredible, and everyone's big yawn, right? And we're now all uniquely going through this really terrible experience with COVID-19, and that narrative for us as a community of bioengineers and cell programmers is going to very much change with the public, right? The public is going to be very aware of how powerful this technology is, and we're going to need the types of folks who you're going to hear from tonight, who are some of the best storytellers and visionaries around engineering biology to help people navigate this, right? I mean, it's going to be, a big question for society. People are going to try to understand, what can we do with this? And I think one of the most important things as a community of synthetic biologists and cell programmers that we can do today is be part of this solution to really this biological event that we have with COVID-19. And that's what we've done with Ginkgo. We've taken our platform, and about 3 weeks ago, we announced we would do $25 million of free work through the infrastructure. We put out an open call to scientists and researchers working on therapeutics, vaccines, diagnostics to COVID-19. Within 3 days, we had about 100 replies to that just coming in. And one of the things that struck me about this is I think a lot of what we're feeling as like the world is responding to this is you're seeing, nations have to, I got to fight for this PPE and this, and it's very like kind of a locally and nationally focused response when it comes to healthcare and public health. But the technology development, trying to develop rapid diagnostics, trying to develop a therapeutic or in the long term a vaccine, that's a global response, right? Whoever does it, we're going to be happy. It doesn't matter, right? And so you're seeing a global collaboration around that, which is tremendously inspiring to me.
But I really like this question that's come in from Lin Chang. And Lin is asking, what do you think is the main bottleneck? And this, Brand, you're going to love this question. So we did following the dinner with Juan and George on diversity, we did a workshop on scenario planning for the future of our species. And one of the things that we spent the most time on was talking about either bottlenecks or accelerants for biotechnologies. And so Lim Chang Kai's question is, what do you think is the main bottleneck limiting the engineering of biology for our needs right now? And I'm going to step back and let our 6 conversants have at that one.
I actually want to pose this to the true experts around me. Do you think it has something to do with the fact that we still don't really have the tools to manipulate biology in all the ways that you would need? I mean, so for example, sequencing the genome was this fabulous breakthrough, and our understanding of genomics has led to so much, but now it's also led to this realization of how much we still don't know about, say, the role of epigenetics or the role of proteomics and so on. And so like there's still a lot more kind of corners to get around, more bends to, go down the road. Could that be one answer to this question?
Yeah, I mean, I take this approach where I tell this to my lab where, we study the brain, and I tell them that the brain the universe had 13 billion years. The brain had 4 billion years to evolve to today, 4 billion years. We hopefully live 100 years if we're being super optimistic. And in those 100 years, we're trying to deconstruct 4 billion years of amazingly complex biology. The fact that we make progress is amazing. So for me, it's like the biggest gap is, it's the knowledge part. And we have to kind of like brick by brick figure out each step along the way. And then once in a while, we get these massive breakthroughs, and it's fantastic. And I think that we'll continue to get there. And I'm an eternal optimist at heart, and I think it's going to be logarithmic, and we'll continue knowing more and more. But again, we're trying to reverse engineer something that's billions of years old on the order of a single career. So we should celebrate those successes that we have along the way, because we're slowly chipping away at the magnificently complicated thing that the brain is, let alone a human body or let alone a species.
Okay. Stephen Hubbard has several good questions. First of all, hi, Stephen. I'm so glad you're here with but I really like this question that's come in from Lin Chang. And Lin is asking, what do you think is the main bottleneck? And this, Brand, you're going to love this question. So we did following the dinner with Juan and George on diversity, we did a workshop on scenario planning for the future of our species. And one of the things that we spent the most time on was talking about either bottlenecks or accelerants for biotechnologies. And so Lim Chang Kai's question is, what do you think is the main bottleneck limiting the engineering of biology for our needs right now? And I'm going to step back and let our 6 conversants have at that one.
I actually want to pose this to the true experts around me. Do you think it has something to do with the fact that we still don't really have the tools to manipulate biology in all the ways that you would need? I mean, so for example, sequencing the genome was this fabulous breakthrough, and our understanding of genomics has led to so much, but now it's also led to this realization of how much we still don't know about, say, the role of epigenetics or the role of proteomics and so on. And so like there's still a lot more kind of corners to get around, more bends to, go down the road. Could that be one answer to this question?
Yeah, I mean, I take this approach where I tell this to my lab where, we study the brain, and I tell them that the brain the universe had 13 billion years. The brain had 4 billion years to evolve to today, 4 billion years. We hopefully live 100 years if we're being super optimistic. And in those 100 years, we're trying to deconstruct 4 billion years of amazingly complex biology. The fact that we make progress is amazing. So for me, it's like the biggest gap is, it's the knowledge part. And we have to kind of like brick by brick figure out each step along the way. And then once in a while, we get these massive breakthroughs, and it's fantastic. And I think that we'll continue to get there. And I'm an eternal optimist at heart, and I think it's going to be logarithmic, and we'll continue knowing more and more. But again, we're trying to reverse engineer something that's billions of years old on the order of a single career. So we should celebrate those successes that we have along the way, because we're slowly chipping away at the magnificently complicated thing that the brain is, let alone a human body, or let alone a species.
Okay. Stephen Hubbard has several good questions. First of all, hi, Stephen. I'm so glad you're here with.
Thank you so much. It's my honor and greatest pleasure to introduce one of the most prolific and imaginative bioengineers of our times, one of the people who was the main inspiration for Sapiens, and George Church. Thank you so much for being on the call with us. And how are you doing?
It's great to be here. It's been a pleasure to interact with you in the past at some of your events. It's a very special time for a very special book and collection of conversationalists tonight.
So let's just jump straight into it. At the times of war or shock, which is relevant to today, scientists and creators are given more freedom to innovate. And it's true, for example, for nuclear weapons and or nuclear research in 20th century. And during the time of the peace, scientists are constrained with the funding, with their cooperation, and with lots of regulations. So how do you think we can possibly match the productivity at the peaceful time, and whether it's possible at all?
Yeah, my personal feeling is that the whole peace-war metaphor is odd. I appreciate why you brought it up. It is often on our minds. I think that we actually have less money during wartime to spend on creativity and productivity, even because we're sending trillions of dollars literally to the bottom of the ocean and into fires. But there is still that nagging question about creativity, and I would say that I think what's important is not so much peace versus war; it's change. It's just the same as in evolution. If the environment's absolutely rock steady, then there's a tendency for organisms to kind of fine tune and settle in for the long haul. But if there's any change, like an asteroid hits, then there's winners and losers, and things start to change very quickly. But the change doesn't have to come from outside the way a war would affect creative processes. It often comes from inside. So, for example, plants will make oxygen. That makes the atmosphere toxic to a lot of organisms. They're winners and losers. A mammal comes about, and that changes the game for everybody. And in the case of getting closer to science and engineering, the internet comes along. That changes everything. It didn't require a war to create that revolution. And the same thing I think is happening now with biotechnology, where we've got a 10 million-fold change, an exponential change, 10 million-fold in a few years. That affects all this.
Yes, very important. Thank you so much for your time.
So it's my great pleasure to introduce and chat with the next speaker, Kristina Goblins. And who I've actually known for quite a while without perfecting my pronunciation of her name. She was did her PhD with Pam Silver at Harvard, and I got to know her then. She was also on the iGEM team, I believe, in 2010, and we even did a paper together on plant synthetic biology, which was fairly new for iGEM, and the team did absolutely. Kristina did a fantastic job. She's now director of biotechnology, Ginkgo, which you've already heard about from Jason. But I think Kristina has a very special role in that I have great respect for, and in communication and writing in general. And I'd like to talk about that with you, Kristina, if that's okay.
That sounds great.
So let's start with this pivoting that Ginkgo has done, combined with the literally creativity that they had even before that pivot, which I think partly is your influence. Flavors, fragrances, foods. I know that you've done some amazing things with cheeses. So what do you see as the silver linings that are coming out of this otherwise horrible event that we're having right now? Are there any creative components that will have a lasting influence? I know that our generation will never forget this, but what could be the good parts?
I think Jason put it really well in the beginning, saying that there's something really inspiring about the way that people have come together to move really fast. There's that expression that people say, like to go fast, go alone, to go far, go together. I think we're actually seeing a little bit of an inversion of that, which is really great. Like that to go fast against this, we actually do have to go together. People are sharing the sequences really quickly. They're collaborating in ways that are much different than typical, like biomedical research happens. People are publishing really quickly on bioRxiv. Things are moving very, very quickly because there's this rush to openness and to new ways and modes of working together, which I hope is something that does last. That we can kind of be more of a community that works together to tackle big problems.
All right, so I think we're moving on now. Great. So it's my sincere pleasure to introduce Juan Enriquez now, who's the managing director of XL Venture Management, which invests in life science companies. So this is impressive. He's the author of 4 books, which is awesome, including his most recent, Evolving Ourselves, How Unnatural Selection and Non-Random Mutation Are Shaping Life on Earth. I have a lot to ask about that. It's my pleasure to meet you, in this case, in digital person. So, how are you? How's your day going?
It's just actually a really interesting day because you get to think about things in terms of what's the future. And I think one of the really important conversations we can have here is what's next. Because what we're doing right now is we're playing like a grammar school soccer game. We're all heading for the ball, and everybody's heading towards COVID. And I think this is like an earthquake that has a tsunami that comes after it, that has shock effects that come after it, and that has all the rest of life to come after it. And I think what's really important is we start thinking about what this all means. Let me start with one thing. We have now disinfected on a scale humans have never disinfected before. And when we've done that in hospital operating rooms, you get antibiotic resistance and you get some really nasty stuff coming out. Mm-hmm. So all this hand sanitizing, all this spraying, all this Lysol, all this Clorox, we may be facing a similar crisis in a year that looks like antibiotic resistance.
Yeah, so it's maybe like trying to stay ahead of that, right? And ideally, do you think that maybe as a species, right, one of the themes of tonight, are smart enough to be able to predict that and stay ahead of it? Since the conversation with wiping our hands and so on and having viruses that mutate faster than maybe we're able to treat it has been in the picture for a while, and I feel like it's been in the limelight now more than probably ever before. So are you optimistic basically about where this can go given this knowledge at hand?
So I am an optimistic curmudgeon.
Fair.
I think there's horrible stuff going on, but in the long run, I think we survive as a species. But the questions that we're asking for humanity right now are absolutely fundamental, because the essay I wrote in the book was about how much we love diversity and how little diversity we have. And in essence, what genome engineers and sequencers have found is there's almost no variation between humans to the point where there aren't races. And one of the questions this epidemic brings up is, what is the consequence of having almost no diversity in a species? And we saw that with the Irish potato blight. When you went from 3,000 potatoes in Peru to 1 potato in Ireland, it's exceedingly vulnerable to a single disease.
Well, there's a quick sample platter. You'll find both the Neo.Life book down below as well as the link for this YouTube, which is sizable. It's 2 hours and 12 minutes long, so it's quite sizable. And that's all we have time for this week. I'll be doing another presentation on the 21st, and I'll be looking forward to seeing you in the flesh sometime after this pandemic is over. In the meantime, I hope you're enjoying these things. Do give me some feedback. Let me know if there's anything you particularly would like to know more about, and I'll be seeing you then. Until then, be safe. Goodbye.